Okay, guys. So we are looking at more things to do with energy. What are the types of energy that we've looked at so far in mechanics? Nahid, an energy type? Gravitational potential energy. Luke, an energy type? Kinetic energy. Hamza? Is that all of it? I think that's all we've got. Yeah, and what other things pop up in our energy equations? Work done against friction. Okay, so those are the three things. I think there's anything else we can add in there. And what we will be adding in now is EPE, elastic potential energy. And here it says that the elastic potential energy stored in a spring or string is equal to the work done in stretching or compressing it. It kind of makes sense, doesn't it? That if you're doing work to make a string get longer, or if you're doing work to make a spring get smaller, whatever work you're putting into it, whatever energy you're using to make the spring get smaller, that must be the energy that the thing has, because if your energy is being taken from your hands that are squeezing it, is being put into the spring. And I've put up there what the formula is for the elastic potential energy. It's lambda x squared over 2L. But we want to think about where that actually comes from. So there's three different ways that we can think about this thing, okay? One of them is kind of like a common sense, sort of like logical kind of approach. One of them will be thinking about areas underneath lines, and one of them will be the more formal way of thinking about it with integration, okay? So we know, we're going to go with this kind of like logical one first of all. We're talking about it's equal to the work done in doing the stretching or the compressing. So what is the formula for work done? Fx, or just the force times by the distance, which in this particular case, the force that we're talking about in order to compress it will be the tension multiplied by the distance that it's being compressed, x, okay? Before you start doing any of the extending, let's talk about extending rather than compressing. Before you actually stretch it, what is the initial tension in the string? 0, because it's not being stretched at all. The final tension after it's extended x will be, what would it be in terms of lambda x over L? Lambda x over L, that's what its tension would be after the extension. So the average tension that it has, because we know that the tension will increase linearly because of the way that we've looked at Hooke's law, what would the average tension be over the course of that extension? What's the average of these guys? Lambda x over 2L. So the average tension is lambda x over 2L. So the average tension times by the distance, which is the work done, the force times the distance, is the tension times x. So this is the tension, which is lambda x over 2L. And you times it by x, and you come up with lambda x squared over 2L. So that's why the elastic potential energy is, it's just a variation of what the work done is. The force is changing, so it's not a constant force, which is why we look at this idea of taking the average of these two tensions that we've got, the beginning tension and the final tension, just to show where that formula kind of comes up with. What we've then got written down here is a diagram that's got like Hooke's law, basically. We've got the applied force, so we've got the tension that's running up along the y-axis, and along the bottom we've got the extension. And we know that as you extend, the tension gets higher until it goes all the way up to lambda x over L. And why is work done the area underneath the line?
It's the same as average tension. No, but T times. Oh, because the graph is linear, like it's a straight line graph. So the area of that will be the height times by the width half, which is lambda x over L times by x times by half, which will give us a lambda x squared over 2L. Yeah,
exactly. And that's kind of like links it back to what we've got up here, but more generally, like the area under any kind of force extension graph or force distance graph is the work done, because the work done is the force times the distance. And if you think about this, we've got a force and a distance, so it's the area underneath. It's a bit like in a speed time graph. The area under a speed time graph is the distance, because distance equals speed times time. Work done equals force times distance.
So why do we use average
we do average tension because the work done is the force that you need to be able to stretch the whole thing out. At the beginning, you don't need much force to stretch it 5 centimetres. But if you've stretched it 100 centimetres and you want to stretch it 5 centimetres, the tension that you require to do that is so much more, you're putting lots more energy into it. Like if you think about an elastic band, it doesn't take much force to be able to stretch it like a little bit at the beginning. But if it's really stretched and you want to make it a little bit more stretched, you have to put in quite a lot of energy to kind of get it over, to get it stretched out even more. So it's because the tension is varying as it goes. And then the more formal way of thinking about this is integration. Well, this integration is going to link to the area of something, okay? So we're now going to say the elastic potential energy, which is the area under this graph, is you're going to integrate between 0 and x. Here's my 0 and x as my limits. You're going to integrate the tension, but this time we're going to integrate it with respect to s. And the reason I've used s here, I've said that the variable s represents the extension at any point during the stretching, whereas x represents the final extension. So we couldn't integrate between 0 and x with respect to x, because x is clearly referring to a numerical value in this place, so we have to have a different variable for the extension, so that one of them is referring to a variable and one of them is referring to a constant, okay? So you can just see that tension would be lambda s over L with respect to s. When you integrate that, you get lambda s squared over 2L between 0 and x, which is just lambda x squared over 2L. So there's 3 different ways of thinking about what the formula is for the elastic potential energy. All you need to really take away from this is that the elastic potential energy is lambda x squared over 2L, okay? So we're going to just do a couple of super quick questions on this, and then we might do just 2 or 3 questions from exercise 3C, and then we'll just do some problems, okay? And this is basically, we're basically finished with further mechanics 1 now, okay? So it says in the first one that we've got here, an elastic string has natural length 1.4 meters and modulus of elasticity 6. Find the energy stored in the string when its length is 1.6 meters. I mean, this is really just substituting straight into a formula. Natural length 1.4, modulus of elasticity 6. What's the value of x? 0.2. So the elastic potential energy is lambda x squared over 2L. Just put it in your calculator and you get your value. So that's 6 times 0.2 squared divided by 2.8. So the elastic potential energy is 0.086 joules to 2 significant figures. Next one, a light elastic spring has natural length 0.6 meters, modulus of elasticity 10. Find the work done in compressing the spring. Pardon? That's E, that's L. Oh. That's my natural length. They're curly L's that we have, yeah? Find the work done in compressing the spring from a length of 0.5 to a length of 0.3. Really just grabbing out the values we've got here. Natural length 0.6, modulus of elasticity 10. What's the value of x? 0.2. So the elastic potential energy is lambda x squared over 2L. .33 joules. So quite a lot more energy is in that one. Why do you think there's a lot more energy in that one?
Because we're going from a compression to an even further compression.
No, we're not going from a compression. Oh yeah, we are. Sorry, yeah. I didn't even read the question properly.
And you were integrated, right?
What am I doing here? I didn't even read the question properly.
I thought isn't it like?
I'm sorry. We talked about. So we actually have to. We could either integrate it, but actually, what we should do is we should look at the energy that's happened to compress it to this, then the energy that's had it to compress to this, and then compare them. That was.
It's directly proportional or something.
It's not directly proportional when it becomes energy though, because the energy has got an x squared coefficient in it. Has got an x squared term in the formula. So it won't be like that. Completely ignore what I do for that first one. We still said that natural length was 0.6 and that the modulus of elasticity was 10. We're going to first of all see what happens for the first stage, just to get it down to 0.5 meters. So when x is 0.1. So the elastic potential energy that got it down to that stage would be lambda x squared over 2L. Sorry about that, guys. Which is 1/12 joules. Then if we have a look at the elastic potential energy now when x is equal to 0.3 to take it all the way to that stage, we get that the elastic potential energy is 10 times 0.3 squared over 2 times 0.6. So that's 10 times 0.3 squared divided by 1.2, and you get 3/4 of a joule. So what do we need to do with those two values to find out how much energy was spent? Nope, not average. We're going to do 3/4 minus a 12th. Okay, so the elastic potential energy to compress from 0.5 to 0.3 is equal to 3/4 minus a 12th, which is 2/3. My brain is like so off right now, which is 2/3 or 0.67 joules to two significant figures. So we can't take an average of this one. We actually have to find out what was the energy that took it down to that compression, what was the energy that took it down to that compression, and then work out, well, what was the energy that took it from this compression to this compression. We can't just do it linearly because of the fact that it's got an x squared in there, okay? So
we could technically like integrate all of them.
Yeah, because this is actually, what we're actually doing here, you're right, we're actually integrating between 0.1 and 0.3. We're integrating lambda, yeah, we're integrating that, right? Lambda x over L. We are just doing that.
Is it not dx?
Well, the reason I've used x in here is because I haven't used x in here, so you could use s if you wanted to. So that's technically what we're doing here. But I just think it's a little bit easier to see it just from using the formula and stuff. Okay? So we're going to have a look at a quick set of questions from exercise 3C. Which ones? I will have a quick look now.